Okay, in this video, we're going to look at another case of SSA that is different than the previous case of SSA. This, by the way, is also sometimes called the ambiguous case. And you'll see why in a minute. So the ambiguous case. So we've got our triangle ABC. So let me draw something here. How about, I don't know, something like that. Angle beta 36.7 degrees. So that makes that B. Maybe I'll put an A there and a C there. That means side A would be 12.4 and side B is 8.7. So it really does look like the last case where I have one complete ratio with my B and my beta and one incomplete ratio with my side A, but I don't know alpha. So that's where I'm going to start. And if I go here, I'll have sine of 36.7 degrees over 8.7. We match up those opposite sides and angles there. With sine of alpha over 12.4 being side A. Go through the algebra a little bit, cross product, solve for it, and I will get sine of alpha equals 12.4 sine of 36.7 degrees over 8.7. Now, last time, in the last video, we went ahead and we went straight into the inverse sine function and got something that didn't work. We wanted to avoid the decimal approximation. In this case, we're going to show what happens when we go ahead and find the decimal approximation of this right-hand side first. So go ahead, pause the video, find the right-hand side approximation of that, and we're going to get sine of alpha equals. And hopefully we're back now. We put this in the calculator, and we went through this, and we got that sine was approximately 0.8518. That's probably good enough. Now, when I do this, what I have to say is, all right, well, I've got an output of the sine function that is positive, and I have to make the note that the sine function is positive. And let me actually write this using more algebraic type terms. That sine of theta is greater than 0 in the first quadrant and the second quadrant. And since we're dealing with oblique triangles, it is possible for this angle alpha to be an acute angle, and that's what it would mean if this alpha is in quadrant 1. But it also could be in the second quadrant if that alpha is an obtuse angle. And we're not dealing with right triangles, so it is okay for it to be an obtuse angle. So that means I'm going to have a couple of cases, and I'm going to have to use reference angles to go ahead and work with this. So I am going to go to the inverse sine function. So I'll have inverse sine of 0.8518 equals alpha. And I will get from my calculator that alpha equals approximately 58.4 degrees. Now, that's that first quadrant acute angle that we talked about. But it's also possible, or that alpha could be a second quadrant angle, an obtuse angle, and that second possibility is going to be the angle that uses 58.4 as a reference angle. So in standard position, 58.4 degrees. If I want a second quadrant angle in standard position, I would want this to be 58.4 degrees, so that it uses that as a reference angle. And the question becomes, how big is that angle? And so I would do a 180 minus 58.4 degrees. And when I do 180 minus 58.4 degrees, I get that alpha could be 121.6 degrees. So, and the truth is, we don't know which one of these it is. That's why it's called the ambiguous case. And that means from here, we have to continue solving and solve the equation, solve using the law of sines, solve the triangle twice. I could almost put a line down here, and I've got to finish solving this 2 ways. So I'm going to have to go through it twice. So let's see. I'm going to summarize what I know right now for each case. I know that on the left side that A was equal to 12.4, and we've got an alpha of 58.4 degrees. We know that B was equal to 8.7, and our given beta was 36.7 degrees. And we don't know our C, and we don't know our gamma, and that's what we have to figure out. On the other side, I know my A, that's not a good color there. I know that my A is still 12.4 because that was given. But my alpha is going to be 121.6 degrees. Beta was given at 8.7, and B was given as 8.7. Beta, 36.7 degrees. I still have to find C. I still have to find gamma. So that's what's left to do. And in both of these cases, I would find gamma first because I can just use the triangle sum being 180. So I can just say gamma equals 180 degrees minus 36.7 minus 58.4. And when I do that, I get 84.9 degrees. And then I would use my law of sines to find angle C. So I can put that 84.9 degrees there. I'm going to use the values of B. Those were my given values, no decimal approximation, so I can be pretty confident in those. So I'm going to say sine of 36.7 degrees over 8.7 equals sine of 84.9 degrees over side C. And so that C would be equal to 8.7 sine of 84.9 degrees over sine of 36.7 degrees. And that's just go ahead, put it in the calculator, calculate right through it, and you would get C being 14.5. So I can go ahead and put 14.5 there. And I've solved one case completely. I have my A, B, C, and my alpha, beta, gamma. Now for the other case, I'm just going to do all the same stuff, just using that other value of alpha. Maybe this would be a good point to pause the video, try to do it yourself, see how it comes out, and then play the rest to see if you were able to do it yourself. All right, we're back. I would start just the same way, finding gamma 180 minus 36.7 degrees minus 121.6 degrees. We go through that process and we get 21.7 degrees. So I'm going to put that 21.7 degrees there. Just as I did before, I'm going to use these values of B and beta with my law of sines, and I'm going to say sine of 36.7 degrees over 8.7 equals sine of 21.7 degrees over C, so that C equals 8.7 sine of 21.7 degrees over sine of 36.7 degrees. You go ahead, you put that in the calculator, you calculate through that, and you end up getting 5.4. And so I have those two cases, and you just present them as cases, and maybe I scroll up a little bit here when you're presenting this as a solution in a problem, and maybe for a test or something like that, and maybe you label each one of these like case 1, in case 2 or something like that, just understanding that. So that's the ambiguous case that you get there. And that's how that works. So I hope you found this helpful. And anything beyond that is just, everything kind of falls into play with this.